Okay, now we're going to jump into a design problem. So what we have here is a cylindrical rod of brass. It's originally 10 millimeters in diameter. Okay, 10 millimeters in diameter. Of course, I knew that would happen. There we go. It's going to be cold worked by drawing. So I'm going to scribble on it. I'm kidding. That's not what it means. It means you grab it and you are pulling it through some small but very, very strong material. And when it gets pulled through, it's big on one side and it gets made smaller on the other. Like that. Drawing. Magic. And you're pulling it to do that. Okay. So the circular cross-section will be maintained during deformation. We want a cold worked tensile strength in excess of 380 megapascals and a ductility of at least 15% elongation. And the final diameter must be 7.5 millimeters. Well, that helps us out somewhat. So explain how this may be accomplished. Well, I'm guessing it's going to have something to do with cold working and heat treatment. So first, let's compute the percent cold work for our material. So we went from a diameter of 10 to a diameter of 7.5. As we said before, if we're in a position where it's, the cross-section is staying the same shape, so it's circular both times, this is just going to be a function of the diameter squared, because pi in that little equation is going to cancel, as is the half. So I get that it's going to be a 43.8% cold work. Whew, that's a lot of cold working. So now we'll need to look at some tables and see, okay, we've got 43.8% cold work. So I go over here and I look at it. I'm going to see if I can trace it up there. Okay, did it there, and I do it right there. Oh, what am I doing? Wrong side. Like right there. And I drag it up to the line. And I see that at this point, my tensile strength is 540 megapascals, which is way more than 380 I needed. However, my percent elongation is 6%, which is way less than I need. I need at least 15, So because of this, I'm going to have to heat treat my material. I have to heat treat my material till it has the right properties. So if I look at this, okay, so for a tensile strength of exactly 380 megapascals, that would be about 12% cold work. For percent elongation of 15, that would be 27% cold work. Now, hopefully what you're realizing here, if you look at this, that these are now our bounds for our cold working. If we're somewhere in between those two, in between 12 and 27, we will both have the tensile strength we need as well as the percent elongation we need. Okay? So it's going to be somewhere in that sweet spot of between 12 and 27. So like right there. Okay? Somewhere in there is going to be our sweet spot. So we need to change the amount of cold working. Well, it's already been drawn. We can't undraw it because the diameter is probably important. However, we can use annealing to get rid of the cold work. Or we can, there's lots of things we can do here. We can anneal it and then cold work it again if we want to. So to meet the criteria for the second deformation step, we'll deform it to 20% cold work. So with this, we're now cold working it down part of the way to 20% cold work. So our intermediate diameter is going to be 8.39 millimeters. Okay, 8.39 millimeters. Like, wait a second, but 7.5 millimeters is what we were going to. That's what we want to go to eventually. That's the end goal, but we don't have to go there in one step. So we're doing that to get ourselves to 20% cold work. And with that, we will have the correct materials when we anneal everything and then cold work it down to the final diameter. So now we can finally show why this intermediate step is necessary. It's necessary because we need a percent cold work somewhere between 12 and 27%. However, to go from 10 down to 7.5, that's like in the 40%. So we have to do it in 2 steps. Our first step right here down to 8.39 millimeters is still going to be more cold working than we need. That's 29.6%. That's going to be too much. So we're going to heat treat it and get rid of our cold work by recrystallization. So we allow it to completely recrystallize. All of our cold work is gone. And then we reduce the diameter a second time. And this time when we reduce the diameter, well, we're reducing it down to a cold working of 20%. A cold working of 20%, which is perfectly within our bounds. So what we did beforehand, if we were to jump back, is we solved for this diameter. The diameter that, if there were no cold working before that point, and we were to go down to the diameter we wanted, would be right in that sweet spot range, right there. And then after doing that, we say, okay, we're going to cold work down to this perfect diameter. We're going to recrystallize by heat treatment, and then we're going to go all the way down again. So that's it for this time. Thank you for listening. Hope this helps you, and I'll see you all later. Have a wonderful day. Bye-bye.